Professor Luo just have already introduced. So my background is actually Wuhan University and then Arizona University in the US, and then University of Cambridge for a postdoc. And then I go to Hong Kong U. I set up the Healthy Cities Lab at Hong Kong U since 2019. And then in 2023, I went back to WHU, to Wuhan University, and continue this Healthy Cities Lab establishment. So in my presentation today, we'll follow the outline. Like, first of all, we'd like to introduce my research background, and then we'll talk about my research contents in the following 3 parts. So part 1 will be the urban land atmosphere interactions, basically for some modeling physics and also some interesting applications. And part 2 is about the human environment exchanges, and part 3 is more like from the engineering part, finding solutions to these urban problems. So of course, as we all know that our world is going rapid urbanization. So this picture is provided by the United Nations that shows the percentage of urban area and also urban agglomerations in 2018. And then next page will show you the similar figure, but it's in 2030. So that's projected by the United Nations in 2030. So, but if you compare these 2 figures, we can see that both the urban area and also the urban size has been increased. So for instance, if you take a look at the red big circle, that means the mega cities with city population of 10 million or more. So by comparing 2030 to 2018, like 10 more mega cities will appear in the world. And 9 of the 10 will appear in Asia and Africa. And in Asia, the urban expansion has its unique characteristic. So it includes not only like horizontal expansion, but also vertical expansion, like with taller buildings and also denser city clusters. So during the rapid urbanization processes, there will be a lot of urban environmental problems. For instance, the urban heat island effect, meaning that the urban temperature is usually warmer than rural temperature for several degrees. And the second problem is the air pollution, which usually occurs in city with a lot of anthropogenic emission, and also as during the rapid urbanization process, like city ventilation, the wind speed in cities have become lower. So the pollution removal ability has also been reduced in cities. And the third problem is the water pollution, and the fourth problem is like urban precipitation and flooding, or we can also say urban rainfall island, if you have ever heard about it. So the urban rainfall island sometimes is initiated by urban heat island, because like the urban heat island making the urban surface hotter, which gives the air more energy to drive the air to initiate the convective precipitation. So in contrast to rural areas, urban areas has its unique characteristics. Like for instance, like buildings tends to be denser and taller. And secondly, there will be a lack of vegetation in cities. And fourthly, and thirdly, of course, there are more and more anthropogenic emissions of like heat and moisture and carbon. So a better understanding of the urban land surface energy and water transport processes is the key to solve these urban environmental problems. And since the urban land surface is the lower boundary condition of the overlying atmosphere, so any changes in the urban land surface will affect the overlying atmospheric dynamics and will further affect the local, regional, and even global climate. And since the cities are clusters to a lot of population, so it means that will enhance the vulnerability of urban residents to the future global climate change and environmental changes. So to solve this problem, first of all, we need to know more about the physics. So the physics about the urban land atmosphere interactions, the governing equation of this is the urban surface energy balance equation, as you can see in the first line. So like the left-hand side is the available energy, R is the net radiation, HF is the anthropogenic flux, and then these 2 terms together, the summation is the available energy. The available energy will be participated into 3 terms, H, including H, the sensible heat flux, LE, the latent heat flux, and G, the conductive heat flux. And to understand the urban surface energy and water transport processes better, we not only consider this governing equation, we need to consider more characteristics of the urban areas. For instance, the urban geometry. So in cities, we need to consider like 3D geometry for that. And then we, so the phase one is that our team has been doing continuous development of a model called urban canopy model. So phase one is just considering energy balance. The second phase considering both energy and water balance. So we consider vegetation, like grasses and trees, and also green roofs in our model. And phase three, we consider the moisture sources with more accuracy. For instance, we will consider building emission of moisture. And also we're currently trying to couple water into, so both vegetation and water is kind of considered as the nature-based solutions, like blue-green spaces. So the last one is the latest work we have done, like, and that paper is just under revision. So the previous page shows you the urban canopy model development, which is the lower part. And then we coupled the urban canopy model with an atmospheric model, the above part. So by coupling the urban land and atmosphere interactions, we can further assess like how urban surface changes can affect urban atmospheric dynamics, and of course, further how that will affect the climate. So, and then now let's take a look at an interesting phenomena in Hong Kong. So, so everyone knows urban heat island. We know that temperatures has been rising, but how about moisture? How about humidity? So, have you ever thought about like is the moisture, urban moisture decreasing, like, or increasing? So the answer to this question could be different, like for different cities. You may say that in cities there are less vegetation, so maybe drier. However, in Hong Kong, we witnesses a long-term increasing trend of urban moisture. So these two figures, the left-hand side showing you the long-term trend of temperature, the right-hand side is showing the long-term trend of moisture, and the black line is the urban station, and the blue and green, the blue and red line is showing the suburban and rural conditions. You can see that urban temperature is usually higher than rural, and urban absolute humidity is always higher than the rural areas. And this is actually the motivation for my first RGC fund. So that is the synergistic effect of urban heat and island, urban heat island and urban moisture island effect. So so this phenomenon, like the urban moisture or specific humidity of urban area, which is higher than the rural specific humidity, we call it urban moisture island. And the abbreviation is UMI. So the global UMI records is that for example, in London, Vancouver, and Crefeld, we witnessed like nighttime UMI. In Tokyo, Japan, we witnessed all day dry island effect. However, in Hong Kong, we witnessed all day UMI effect. So we would like to know why. So the mechanism behind UMI lacks deep exploration. And then we actually developed this UCM model to consider trying to figure out like the moisture mechanism behind. So this dynamic building tree air interaction has been considered in the latest phase of our UCM. First of all, we develop a new building emission model. Usually, when we are talking about building emission, most of us talk about the sensible heat or like heat emission, but we don't mention like moisture emission. So here we divide the emission into sensible and latent heat part. And secondly, we introduce a new, an enhanced tree module. So we can consider the evapotranspiration effect, shading effect, transmission effect, and aerodynamic resistance effect more realistic. So by introducing these two new modules, this urban canopy model can resolve our like urban moisture with more accuracy. And this model has been tested in Hong Kong, 2 stations. The first one is SSP, Sangsuipo, and the second one is HKO, the Hong Kong Observatory. And our comparison, the model simulation comparison against measurement, they show very good results, and the accuracy of HNLE has been improved by 40 to 60%, especially for the latent heat part. by comparing to other urban surface models. And then after model evaluation, we conducted some model sensitivity analysis to try to explore like the impact of like the urban form, building emission, and also vegetation evapotranspiration on the urban heat island and urban moisture island intensity. And if you, for instance, the first figure shows that most of the time, we can witness UHI above the axis. But sometimes when we see the red line, when the aspect ratio is equal to 8, which means that the building is really tall and the street is really narrow. And then in that case, we can witness urban cool island, UCI. So this is also an interesting phenomenon. And the second paragraph in the first row, we can see that usually at nighttime, UMI occurs and UDI will occur at daytime. The first row only shows the impact of urban form alone. And if we consider more realistic factors, including building emission and vegetation evapotranspiration, like the figure B1 and B2, you can see that both lines have been shifted above. And by considering building emission, especially building emission, like all the cases, or all the aspect ratio cases have been moved to UHI case. No urban cool island happen anymore. And then B2 figure shows us that if you follow the dash red line and the solid red line, when the aspect ratio is equal to 548, you can see that at this occasion, some UDI phenomena has been shifted to UMI phenomena. The reason behind, we think that the UHI, the synergistic UHI and UMI effect may be maybe as follows. So since the urban heat island has making the cities warmer, so UHI can induce more evapotranspiration and also will prohibit dew, especially like at nighttime. And also for example, in Hong Kong, we have like more and more taller buildings. The ventilation has been weakened, so the wind speed in the city has been lower and lower. So that kind of like reduce the moisture removal ability. And so that kind of side is the mechanism. And then we also apply a regional climate model to consider like the fine resolution land use land cover data set. So we divide the urban land use land cover like into different categories following the local climate zone standard. So for instance, like LCZ1 is a compact high-rise area. These areas like around the Victoria Harbour, like these two sites, they are considered like more LCZ1 concentrated near the Victoria Harbour. So then we incorporate these fine resolution data into a weather research and forecasting model, is a regional climate model, and to evaluate the spatial temporal variation of temperature and humidity. And specifically by coupling into this regional climate model, we can assess the impact of topography. For instance, like the right-hand side, the left-hand side figure is just showing you the model settings. The right-hand side showing you the wind from south to north. As you can see that the sea breeze can always bring a lot of moisture inside. And then if there is some mountains, we should also consider the mountain blocking effect. And that's kind of a regional impact. For local impact, we need to consider like the urban form. We use the aspect ratio to denote the urban form. So for this LCZ1, something like compact high-rise areas, moisture can not be easily removed. So the second part is that so the part one just showing you how we model temperature and humidity, how we model this hot, humid climate. The part two, we are trying to explore how this hot, humid climate affect human health. So the information of this part is connected to my second GIF account, GIF fund. So first of all, we developed human environment adaptive thermal stress model, where we using the abbreviation HEAT model. And in this model, first of all, we developed a new protective face mask model. Well, you may think that's kind of like very surprising. Why you see face masks? Because this funding it is approved during the pandemic. So during the pandemic, I got fund named development of face mask inclusive thermal stress prediction and warning system. Because at that time, I was working in Hong Kong, and then I feel that when everyone wear masks, especially when working outside the sunshine, when we because Hong Kong is in Hong Kong Island, we usually need to climb, and so we find that when we are climbing, we feel hotter. So so the second innovation here is that we consider it kind of like one of the few models which consider topographical impact. So these two modules are quite new. So the first one we developed a new protective face mask using we actually have provided two methods. One is based on energy balance method. Another one is based on the computational fluid dynamics model. And the second one we consider a new topographical module for mountainous cities. So this figure just showing you some experimental results. So the left-hand side just showing a student doing different activities, standing, walking, climbing. The first row is doing these activities without using a mask. The second row shows you like the student doing these activities with his mask, and then he will take off the mask and we will use an infrared camera to capture his face temperature. So you can see that by increasing the activity levels, the face has been like more red, so hotter and hotter. Here we can also see kind of like a slope. So the x-axis is slope, and the y-axis is the physiological sensitive temperature (PST). We can see that about like well, I didn't remember the exact figure. Probably 5 degrees per 10 slope degree. And if you still remember, I introduced the urban canyon model, and then we coupled this human module into the urban canyon model. So this work is that we conduct a pioneering work by adding a human module into a UCM. Before our work, there is no one doing like this, like coupling a human module into the UCM. So and then we consider realistic human environment exchange in the street canyon. For instance, we consider this relative shading effect, and also the transmission and shading effect of the trees, and so on. And we also consider dynamic human thermal regulatory response to microclimate change. So if you see some these parameters like showing, and these arrows showing near this human body, just showing you like, for instance, RES means respiration. With respiration, we can release heat. And E is evaporation. So when you have sweated, and the evaporation of your sweat will make you cool. And C is the convection. So if you have some wind breeze, you may feel cool. The M is the human metabolism, and which is connected to like different age and different weight, and considering different activities. So this UCM and his coupling model has been validated also in Hong Kong. We in Tianzadui, in a street, we conducted some field experiments, and then compared our model simulation with field measurements for air temperature and air humidity in the top arrow, and the skin temperature of the volunteers in the second row. So based on this UCM heat model, we can calculate like human heat balance results. For instance, this net heat storage, net radiation metabolism, convection, evaporation, and respiration. So like if we see the first figure, like above the zero axis, above that is the energy input, and below the zero x-axis is energy participation. And we find that the RNH, the net radiation, is the most important most important factor that will affect human thermal stress. And therefore, we further investigate the shade effect. When we talk about shade effect, we consider not only the shade effect of buildings, but also shade effect of trees. And we propose this idea of like shade optimization. So we propose like right shade, right place and right time, right there. And then we also consider the impact of human factors, including the BMI, age, and walking speed and clothing. For instance, the first figure is the BMI, which means that when the PST will increase, the human stress will increase with the BMI. And the second figure is showing the relationship between walking speed. As you can see that the optimal walking speed is about like 0.5 to 1 meter per second, showing you it's kind of like you're doing you work leisurely. If you walk too fast or too slow, you may feel hotter. And then the figure B shows you the heat exposure for people with different ages. For instance, like for older people, they may have like longer heat exposure. And figure D shows you like for different, like for cool surfaces, if we change the albedo of like, for example, ground, wall, roof, and of course you can change your clothes. If you change your clothes from a dark color to white color, you also change a lot for your human thermal comfort. We also trying to couple this heat model with a regional climate model. So the procedures like this. First of all, we incorporate the fine resolution urban land use land cover data into the regional climate model, and then we predict high resolution spatial temporal variation of temperature and humidity. And this spatial variation of temperature and humidity will be an input for the heat model. And then further step is that we will predict the heat stress map for the whole city. So here is a heat stress map for the whole Hong Kong. And we also collect some fine resolution data, such as the road network of Hong Kong, so that we can further predict the high resolution road map of heat stress, so that, for instance, we want to plan for our trip, right? If we want to, the starting point is A to B. We have several routes, and then we can do some route optimization to choose the most comfortable one by doing some calculations. So that's all for the part 2. Part 3 is like I'm trying to discuss several solutions to the urban problems. The first of all is the nature-based solution, like the urban green-blue spaces. The first one is like the city greening optimization. So if we consider a city moistening phenomenon, how do we consider about that? So here is an interesting analogy provided by Professor Li at Hong Kong. When I discussed with Professor Li, like he said that when he was a childhood, he always played in the field ground, like in a cornfield. In cornfield, we usually feel like we're very hot and humid, and also with stagnant wind. And if we are in a forest canopy, and it's usually cool, fresh, we can always feel cool and fresh and calm breeze. So when we are doing our city greening, the cornfield phenomenon is what we want to avoid, and this forest canopy is what we want to encourage. So that leads to our consideration, like we don't want like a cornfield city. Do we really want it? We don't want it, right? And the right hand side figure, the first one is a concept provided by I think it's city of Beirut. The Beirut Wonder Forest. They want to do a 100% city greening for the whole city, and so it's a green city like that. Do you like that? Do you like a city like that? So maybe not. So we need to think about where to green, and of course, and or in other words, to do the city greening optimization. So when we are thinking about city greening optimization, we can think about the tree types and also the scales of this green space. The objective is that we want a good ventilation in the city, and we want less trapping of solar heat. We want effective moisture removal, and we want to like select the right trees. And in Hong Kong, we did some case studies. So the left-hand side shows you the 9 common tree species in Hong Kong, And we divided these tree species into 3 types according to their characteristics. Like first type is that with large crown area and high crown height. And type 2 is like small crown area and high crown height. And type 3 is a small crown area and low crown height. And we would like to ask the 3 questions that for a given urban form, like how do different tree species perform? And question 2 is that for a given tree species, how does it perform in different urban form? And these 2 questions goes to question 3, like how to select optimal tree species for different urban form. So our preliminary results show us that, for instance, like for a street canyon with low aspect ratios, we might need to select the tall trees with large crown area. And for the street canyons with high aspect ratio, the optimal tree could be like tall trees with small crown area. So some preliminary studies. Of course, we can like consider like more characteristics of trees. In addition to trees, of course, green roof is another like green infrastructure, and white roof is also a popular concept. We assessed the regional climatic impact of green roof and white roof. For instance, this study is conducted in over Phoenix City, a semi-arid city in the US. The result, we use a regional climate model to simulate that, and we found that both roofs, both green roof and white roof, can help us to reduce the surface sensible heat flux by about like 150 watts per square meter. And when we're comparing green roof and white roof, green roof can add extra moisture into the air. And another interesting result of this study is that we found that the convective precipitation initiation probability could be changed in the city and in urban and suburban areas. For instance, we can think about this question: if we change all the conventional roof to green roof, to change all the conventional to green roof in the city, then what will happen to the city climate? And our simulation, like at Phoenix, a semi-arid city, shows us that the convective precipitation probability will be reduced in the city core, and the convective precipitation probability will be enhanced at suburb. That's kind of some implications for the urban precipitation effect. And then another like urban heat mitigation strategy is using the urban blue space. This here shows you a case study in Shanghai. I presume like everyone, not everyone, like probably most of you have been to Shanghai, and you usually probably go to the city core, and then you probably you didn't know that there are so many rivers in Shanghai. The left-hand side shows you the river network in Shanghai. If you just go to the city core, you couldn't find it. So but we find a 5 resolution urban river, and find that Shanghai is actually covered by very, very rich river networks. So then we investigate this question, like how can urban river networks shape city climate? So before our study, when the scholars doing the research about urban blue space, they only select one river or 1 or 2 rivers, a few rivers. But here, this is the first study that we considered a river network. So we try to figure out like how river networks will shape the city climate. And the left-hand side shows you the river canal, like in different kinds of urban forms. So I showed you like the different urban categories, the LCZ1, local climate zone 1, 2, 3, 5. So that means the different combination of building height and street width. And here, of course, different street width also means different river width. So in this study, we do a multi-source data fusion. So we integrate like remote sensing data and also fixed and mobile monitoring. We conducted like a month of field experiment in Shanghai, and so this is conducted in the wide river is a Huangpu River. It's kind of like the mother river of Shanghai, and the narrower river is called Suzhou Creek. And that is kind of like grandmother river of Shanghai. So our study area is just in the core center, and the third row shows you our experimental equipment. So we use the motorcycle, electrical bicycle, and cars, and also boats to do some fine resolution monitoring in Shanghai. And our results are like briefly summarized below. So we find that urban rivers can be cool sources and wind corridors. And secondly, rivers compared to trees are fixed usually. And the position cannot be moved, but the rivers can flow and carry cool water from upstream. So for instance, if the river is coming from a rural source, rural area, then the water might be cooler. And if a river is passing by an urban park, for instance, below a tree canopy, then the water can also be cooler. And this river flowing characteristics can also bring some cooling effect for the downstream. And thirdly, we find that the river width and the confluence can significantly affect the river cooling efficiency. So one river meets another river, or like one river meets another two rivers. In this confluence, the cooling effect might be enhanced. And of course, like we want to consider about the blue-green configurations. So the riverside vegetation should also be well planned to ensure good ventilation and moisture removal. For instance, like beside the river, if you plant very dense trees, it may trap a lot of humidity. And so although you reduce temperature, we increase the humidity. We need to consider about the balance of the temperature and humidity. In addition to urban rivers, we have also done the study about urban lakes. So we developed like a multi-scale water energy coupled CFD model. The above figure shows you the urban lake recirculation. The left hand side is a lake area. So in the urban area, usually we have like a lot of thermal plumes going up because of it's hotter in the urban area and it's cooler in lake area. So that will induce like a circle for like we call it like a lake breeze circulation. And this lake breeze circulation is very important when the regional wind is very calm. So in calm wind conditions, which means that at regional scale, the wind speed is nearly zero, so you cannot feel any breeze. But this thermal contrast can bring us extra cooling effect just through this thermal effect. And based on this study, we investigate the impact of different urban planning, lakeside urban planning. Like for instance, if we want to, the first column is a fixed area. We do the urban expansion, the fixed area, but we change the building height. We change the building height, so here it's kind of like increasing building height, but reducing building numbers. So this is the first scenario. The second scenario is that we fix the building density, but we increase the urban area. And the third column is that we fix the building height, but we change the building density and also the building covering area, and to test like which condition is the most thermally comparable one. And we find that if we're doing like urbanization, if we do horizontal growth, meaning that increase in the urban area could be better than vertical growth, meaning increase the building height, or like infeeding growth, meaning that you increase the building density under this specific condition. So if under other conditions, we may need some other consideration. Here, I'm only talking about calm wind conditions. In addition to these blue-green strategies, we also need to consider about energy efficient buildings. So for building emissions in the compact high-rise cities like Hong Kong and Singapore can be up to 400 watts per square meters. And in the 400 watts per square meter, 60% will be sensible heat and 40% will be latent heat, which can lead to a UHI of 1.6 degree and a UMI of 0.9 gram per kilogram, respectively. So the question is that how to reduce anthropogenic emission. We may have like two ways. First of all, we would like to use the energy efficient air conditioning mode. So that means that I just talk about like the moisture effect. So if for drier conditions, our tolerance to temperatures is higher. So sometimes if we reduce the indoor moisture, our temperature, our room temperature can be slightly increased. So in that way, we can find the optimal temperature and humidity combination to encourage this energy efficient air conditioning mode. And the second way is that we just forget about using air conditioning and just using natural ventilation. For some cases, we can do that. For instance, for some European mild climate cities, we can do natural ventilation only. So this just reminds me of these two projects that I have participated in Cambridge. The two projects at Cambridge include, the first one is called MAGIC, meaning managing air for green inner cities. And the second one is called low cool, meaning like low carbon heating and cooling of cities. So the left-hand side shows, because it is a big team and it's a big project, about like 500 million UK pounds, I think that. So it's a big team, and then it's including expertise from different areas. For instance, we kind of integrate all the knowledge together, like the left-hand side circle. So we integrate the climate, building energy modeling, energy plus, and also we include wind tunnel, water tunnel, and computational fluid dynamics model, and reduce auto model, data assimilation, etc. So we're trying to, as you can see that, like the dashed blue line showing you the indoor condition has been linked together, and red solid lines showing you the outdoor condition has been linked together by integrating all these modeling tools. And the project objectives are listed at the right-hand side. So the major project, the objective of the major project is to develop a fast-running urban fluid mechanics modeling tool for and the study areas London. And the local project is the objective of local project is to calculate the impact of natural ventilation on building energy. And finally, we would like to propose some building retrofit design. So here, just show you some figures and study areas about these two projects. For the major project, the study areas like this is in central London, and we also select a study building in the center of this study area. So we conduct we build a lot of building blocks and then conduct wind tunnel experiments, and that is in University of Surrey wind tunnel. I think it's a very famous tunnel in the UK. And then we measured like a lot of stuff, specifically the pressure coefficient for different wind angles. And then we incorporate this information. We integrate this information into building energy simulation, the energy plus model. And by coupling the wind tunnel and energy plus model, we kind of like improve the model simulation of the indoor temperature and humidity. So the building energy consumption can be saved up to 5.6 kilowatts hour per square meter, and building carbon emissions can be reduced by 3.23 kilogram carbon dioxide per square meter per month. The result is for London. And then for the low cool project, we conduct the natural ventilation studies in Hangzhou, a subtropical and monsoon climate. So first of all, we assess the wind effect from different directions, like north wind, easterly wind, south wind, and westerly wind. And then we found that in the north facade, like we can introduce the probability to introduce fresh air is highest. So we're trying to doing some building retrofit design based on our CFD simulation results. So this building retrofit design is proposed by Professor Alan Shaw at Cambridge. So he proposed that we do the cool air intake via wind catcher in the north facade, and then he is also proposing some chimney design so that warm air can be removed via chimney, and he also designed some new sun shading structure. So that is showing in the next page. So the right-hand side is a design structure. So incorporating like wind catcher and also the chimney, and also a new sun shading structure. So that's kind of to the end of to the summary of my talk today. So my ongoing project at Wuhan, I just want to using a few pages to talk about that. So first of all, since I'm supported by like the National Excellent Young Scientist Fund, I got a lot of money, so I got a lot of money to buy equipment. So first of all, I purchased an ethical warehouse tower, and I purchased some wind lidar and drone. So we would like to do, and we also would like to establish some meteorological monitoring system over green roofs. So in short, we'd like to do the sky to ground monitoring system in Wuhan. And in addition to field experiment, of course, we would like to do comprehensive simulation studies based on Wuhan. And the right-hand side just showing you the condition of Wuhan. So Wuhan is a city with hundreds of lakes. So that gives us a perfect test bed to study the impact of lakes. And these lakes, there are some urban planners propose that probably these lakes can be natural wind corridors. So you can see there are like 6 angles there. This is what they propose as wind corridors in Wuhan. Well, we doubt about that. We're not sure whether these wind corridors make effect or not. We want to assess that. So based on the dense urban observation network, so in 2022, a few years ago, the Wuhan Meteorological Bureau had set up like dense urban observation network. Like here now, before 2022, we only have like 5 meteorological stations at Wuhan, the national scale weather station. After 2022, we have 180 urban weather stations. So we have dense urban observation networks. You may probably think, oh, you have so many big data. Then of course machine learning appears. So of course we will apply that. And then we also would like to do high resolution regional climate modeling. And we also would like to integrate physical simulations and deep learning. And we would like to assess the unique phenomena like a city with hundreds of lakes, and to do the wind corridor analysis and how the urban blue-green strategies can help to mitigate the urban heat and moisture island effect at Wuhan. Just one page just showing the Yangtze River simulator. The Professor Xiao Yuluo knows that for this Hong Kong trip these days, another senior professor come together with me. He makes another talk in Hong Kong U this morning, and the key topic is the development of Yangtze River simulator. So for the Yangtze River simulator, it incorporates like for instance, wants to investigate how show us how the past, present, and future of Yangtze River. Specifically, the objective of Yangtze River is to the Yangtze River simulator is we would like to provide a tool to do more accurate urban flood forecast. So by integrating meteorological information, like remote sensing information, many monitoring information, and etc. Because this is also a very, very big project and integrates many teams. So I would like to tell you the final objective. The final objective is to kind of to maintain the water security, meaning that we need to have maintain the water quantity, meaning that to mitigate urban flood, water quality to keep our water clean, and also water ecology to like have a low carbon Yangtze River and low carbon cities along the Yangtze River. So so at Wuhan University, I'm in the big team of that senior professor called Professor Jiyun. So his representative work is Yangtze River simulator. Like how I can collaborate with him is that I would like to enhance the urban module, especially urban agglomeration module in the Yangtze River. So that we probably have more accurate urban predictions based on the big framework of the Yangtze River simulator. So we can kind of to support the green development of urban agglomerations along the Yangtze River. And if you still remember, probably you didn't remember because that is showing in my background in the second page. So I have like multidisciplinary background. So including like hydro and water resources, urban climate, building science, etc. And so this figure shows you the link. So my main focus is the urban environment issues, and I would like to integrate like climate, water, energy, ecosystem, building, and human. All these, I would like to integrate all these factors and then to foster the urban green development and urban environmental sustainability. I think that's all for my talk today, and I welcome collaborations, and that's all. Thank you.
Thank you, Professor Song.